This is the level 1 capstone of the S32K Mastery Path, and it's the real thing. A CAN sensor node running on a 10 millisecond real-time schedule, transmitting a live status frame, accepting commands over the bus, and enforcing a genuine safety timeout in firmware. We're going to walk it step by step: the requirement, the architecture, the exact CAN bit layout, the state machine, the code, the bench test plan, and a race condition the lesson itself leaves you to solve. Here's the spec, stated precisely, the way a real requirements document would: sample a temperature sensor over ADC every 10 milliseconds, filter it and run plausibility checks, transmit a CAN frame with a defined signal layout every 100 milliseconds including a validity flag and an alive counter, receive a command frame that sets a target PWM duty, drive that PWM output toward the target with safe clamping, and feed a watchdog, but only when every task reports healthy. Everything in this node hangs off a single 10 millisecond hardware tick from the LPIT timer, the same cooperative scheduler pattern from the timers and PWM module, now carrying a real payload. The sensor task, the command watch task, and the output task all run on every tick. The CAN status transmit only runs on every 10th tick, giving you the 100 millisecond cadence without a second timer. This is the actual data flow: ADC into the sensor task, into a shared app_state struct holding temperature, validity, the alive counter, and the PWM target. The CAN transmit task reads that state out to the bus every 100 milliseconds, a CAN receive path writes commands back into it, the output task drives the PWM peripheral, and only if sensor, command, and output health are all true does the loop feed the watchdog. Now the part that makes this a real vehicle network node, not a toy: the exact bit layout of both CAN frames. Get this table wrong in a real vehicle program and you don't get a compiler error, you get a bus full of nodes silently misinterpreting each other's bytes. The status frame, ID 0x310, goes out every 100 milliseconds on 8 bytes, bits 0 to 15 carry coolant temp as assigned 16-bit value scaled by 0.1 degrees Celsius, bits 16 to 31 carry supply voltage in millivolts, bit 32 is a sensor valid flag straight from the plausibility check, and bits 36 to 39 are a 4-bit alive counter that wraps 0 through 15 the receiver's proof that this node hasn't frozen and is resending stale bytes. The command frame, ID 0x311, comes in from the bus. Byte 0 is PWM target PCT, 0 to 100%, and bits 8 to 11 are the sender's own CMD alive counter. And here's the safety critical line in the spec: the node treats that command as stale after 300 milliseconds without a new alive counter value 3 missed 100 millisecond cycles and falls back to a safe state. That one sentence is the whole reason this capstone is interesting. The state machine makes that safe state rule concrete. INIT runs once, clocks, pins, ADC, CAN, and timers come up, and outputs are forced to the safe state before any of that PWM at 0%, so there's no window where an uninitialized peripheral could drive something. Only after that does the tick start driving tasks. From normal, 3 consecutive implausible sensor samples drop the node into fault, forcing output to 0%. It takes 5 stable samples to earn its way back. And separately, if the command goes stale past 300 milliseconds, the node enters CMD_stale and holds the last known good target, clamped a distinct failure mode from a sensor fault, with its own recovery path. Here's the main loop that actually implements that schedule and see. Notice what it does not do: it doesn't block, it doesn't call delay functions, it just checks whether the tick counter has advanced since last time through the loop, and if it has, it runs exactly one 10 millisecond slice of work. App_state_t is the single struct every task reads and writes: temperature, validity, PWM target and actual, and the command's alive tracking. Main forces output safe before INIT even finishes, then loops forever. Each new tick runs sensor, command watch, and output tasks. Every 10th tick also transmits the CAN status frame, and the watchdog only gets fed if sensor, command, and output all came back healthy on that same tick. Command underscore watch underscore task underscore 10ms is where the 300 millisecond timeout actually lives. If the RX handler updated the alive counter this tick, it resets the age counter to 0 and adopts the new target, clamped to 0 through 100. If not, it increments that age counter, and once it passes 30 ticks 30 times 10 milliseconds is 300 milliseconds, it forces the PWM target to 0 and reports itself unhealthy. That's the Module 7 signal timeout habit, made concrete in one function. Now the actual task implementations. 3 functions, each one owning exactly one responsibility, each one returning a bool the main loop uses to decide whether it's safe to feed the watchdog. Sensor underscore task underscore 10ms reads the ADC channel. If the raw value falls outside the plausible range, it counts consecutive faults and only marks the reading invalid after more than 5 in a row, so one noisy sample doesn't trip a fault, but a genuinely dead sensor does. Otherwise it resets the fault counter and runs the reading through the NTC lookup and filter from the ADC module. Can underscore TX underscore status underscore task underscore 100 ms packs temperature and voltage into little endian bytes, and packs the valid flag and the incrementing alive counter into a single byte using a bit mask and shift, exactly matching the bit table from earlier. And can underscore on underscore command underscore receive the RX callback rejects any target above 100% outright, then writes the new target and a live value into globals and sets a flag the command watch task consumes on its next pass. Output underscore task underscore 10ms is the last line of defense. It computes a safe target of 0 whenever temp underscore valid is false, no matter what the command frame asked for. Then slew limits the actual PWM by exactly 1% per 10 millisecond tick toward that target, so the actuator never jumps instantly and it always returns true, because an output stage that reliably reaches a defined state is, by this design's own logic, healthy. A design isn't done until you know how you'd prove it works on real hardware, with a real CAN adapter, a PCA and USB, a candlelight dongle, or a second S32K board actually on the bus. You log the bus with CAN dump and confirm 0x310 arrives every 100 milliseconds with its alive counter cycling 1 through 15 without skips. You send a CAN send command with target 50 to request a 50% duty and watch PWM actual PCT slew up over successive status frames. Then, the test that matters most, stop sending 0x311 entirely, and confirm PWM decays to 0 within exactly 300 milliseconds of the last accepted command. 2 more steps close the loop, disconnect the thermistor and confirm sensor valid flips to 0 within 5 samples, forcing PWM to 0 regardless of the command. Then, in a debug build, deliberately stall the sensor task for over 100 milliseconds and confirm the board actually resets, with the reset-cause register reporting watchdog not power on. That's proof the supervision chain is really wired, not just present in the source. The cheat sheet distills it to one page: 1 10 millisecond tick drive sensor, output, and watchdog. Every 10th tick drives can transmit. Command timeout is 300 milliseconds sharp. Outputs are forced safe at boot and on any sensor or command fault. Slew limiting caps actual PWM movement to 1% per tick, and the watchdog only gets fed when every task, not just some, reports healthy. The lesson closes with an exercise, and it's not busywork, it's the real skill this whole level was building toward. It asks you to write a one-page design note, the CAN table, the state diagram, and, most importantly, a known limitations section that answers one uncomfortable question honestly. Is there a race between the RX callback and the main loop reading G_CMD_ target? Look back at the code. CAN _on command received can fire from a CAN interrupt at any point mid-tick, writing G_CMD_ target and G_CMD_ alive as plain globals with no lock, while command _watch task _10ms reads them from the main loop. On a Cortex-M with aligned word writes that's often benign in practice, but often benign is not the same as proven safe, and the lesson deliberately leaves that gap open. The second question is just as real. What happens if two nodes on the same bus get accidentally flashed with the same CANID? Answering both honestly, in writing, before anyone reviews your code, is the actual discipline this capstone is testing. This capstone is small enough to build in a weekend and honest enough to teach the real shape of automotive firmware, a fixed real-time schedule, a precisely specified bus protocol, a safe state that's genuine, not decorative, and a bench test plan that proves every one of those claims instead of assuming them. From here, Level 2 picks up exactly where this capstone's rough edges are FlexCAN mailboxes, FreeRTOS, and UDS diagnostics to go close them properly. Full lesson, the complete CAN layout tables, and every line of code shown here are at the link on screen. Go build it, then go find the race condition yourself.